Thank you, Mr. Chairman. Ladies and gentlemen, it is my pleasure to present you this, I will call it preliminary study. It is on numerical simulation of fatigue crack growth in friction stir welded T-joint made of aluminum 2024 alloy. This is a part of a large project that we started a couple of months ago. It will consist of some experiments. Toward that aim, T-joint specimens were produced. And you may see at the sketch below different types of T-joints. The one that we will use was produced as type A. Now, before we started experiments, we wanted to check what numerical simulation can give us. The most interesting question for us was if the crack would grow only to the base plate, or would it deviate and go at least partially through the stiffener. We are not considering only T-joints, we are actually considering plates with several stiffeners, as it is a more real structural case. Now, to go back to numerical simulation, nonlinear finite element code abacus was used. That means also Morpheo as a post-processor. And since this is a welded joint, we have modeled different parts of welded joint, but since this is still at the beginning, all properties, as you will see, are taken as being the same, at least for the crack growth properties. So, more details. This is how it looks like schematically. There is the base metal, heat affected zone, thermomechanical affected zone, and the nugget. Once again, the same scheme, more realistically, at least in these two above macro photos, and simplified schematic presentation. These are the properties. That is quite important. You may see now that they are a bit different in the sense of elastic-plastic properties, so tensile curves, stress-strain tensile curves. This is the same but given in a format which is used in abacus. And finally, for the fatigue, as you may notice, we so far have been using the same constants for Paris law in all our simulation. That will be first important step in advance calculations when we make it. So probably next conference will present that. Now for the numerical simulation and for the fatigue crack growth, we are using extended finite element method. This is post-processing of software abacus done in Morpheo. A couple of elements that can be used, and a couple of fracture criteria that are at our disposal. And now the simulation as it is. This here is the mesh, that is step number 1, to create 3D model. Then step number 2, defining materials, mechanical properties for all different zones. As I told you, they are different in elastic, plastic, static loading, but not later in fatigue crack growth. Then introducing the initial crack, which is shown here. Then introduce loading and boundary conditions, of course. Finally, generating the mesh, which is given here. I will show graphical results soon as well, but first to make an overview of results and a small discussion about them. So what you will see graphically is load cycles versus crack climate. This is as for the fatigue crack growth. And then also for the fatigue crack growth, you will see how stiffeners indicate the redistribution of the load, and thus they would increase, of course, as we expect them, the structural life of welded joint. You will also see that faster crack growth occurs after approximately 70,000 cycles, so this can be understood as a kind of life limit in this case. Of course, it's just numerical simulation that needs to be experimentally verified. Then, what was most interesting for us, propagation of the crack through the structure. We have noticed change of its direction. It could be clearly seen after crack propagation reached the stiffener, because it has grown vertically for a while and then once again horizontally through the base metal. And this we have related to the shear stresses, which are of course immanent for a structure like this. So the curve that I mentioned is given here, crack propagation steps and number of cycles. So at about 70,000, you may notice a relatively significant increase in crack growth rate. So from engineering point, it's a bit arbitrary, but from the engineering point, you may think of 70,000 cycles as being critical for this specific welded joint or specific structure. Now here, you can see a couple of steps as produced by Alcus and Morfell. This is step number probably 0. Yeah, step number 0, just stress state around the crack with static loading, because it's step number 0, and I probably forgot to mention, but loading was relatively low, amplitude was 10 megapascals. So this is why the stresses are relatively low. Now step number 12, which, if we go back, is approximately here. So we are already deeply in this region, in the critical region. Step number 12 indicates that crack growth is just about to reach the stiffener. Crack tip is just about to reach stiffener. Step number 22, even closer. So to go back to check, step number 22, it is quite critical, at least from the point of view of numerical simulation. And then somewhere around step 33, one may notice, if not here, then certainly here, that crack started propagating through the stiffener and then also continued to propagate along the base material, along the horizontal plane. So, to conclude this relatively short presentation, as I told you more or less that these are preliminary results, the main results and conclusions are as follows. First, numerical simulation can be used to determine the right time to withdraw a crack component from operation, because unstable crack propagation would occur as I explained, but we still need, of course, experimental verification to quantify this. This is, how to say, preliminary conclusion. The other one, which was actually more important for us, at least from the point of view of numerical simulation, crack propagates in different directions. Base material and stiffener, this is due to shearing stress and redistribution of stress intensity factor. Thank you.